In this circuit, we want to determine the differential equation governing V of t, the voltage across the 0.5 farad capacitor. For t less than 0, this circuit is closed. The switch opens at t equals 0. So to find the differential equation for V of t for t greater than 0, we look at the circuit with the switch in the open position. So circuit, so we have our 8-volt source, 4 ohm resistor, another 4 ohm resistor, 2 ohm resistor, and our capacitor. And here is the voltage we want, V of t. This switch is an open circuit, so it doesn't affect anything in this circuit for t greater than 0. Now, I'm going to need the voltage current characteristics for the capacitor, so let's label this current, positive current entering the positive voltage terminal. It's 0.5 dV by dt. Now we're ready to go ahead and start applying KVL, KCL, and Ohm's law. So let's start out by doing KCL here at node A. If I call this voltage difference here V sub A and use this as my reference 0 volts, I'll get VA minus 8 volts over 4 ohms plus VA over 4 ohms plus the current through the 2 ohm resistor is the same as the current through the capacitor, which is 0.5 dV by dt. That sums up to 0. That's fine. But we have an extra unknown, VA, in here. We have one equation and two unknowns. We need to eliminate VA. Let's do KVL around the rightmost loop. So we get VA is equal to 2 ohms times the current, which is 0.5 dV by dt, plus the voltage across the capacitor, which is V. So these cancel, and I get VA is equal to V plus dV by dt. Now I can plug that in up here, so I get 1 over 4 ohms times V plus dV by dt plus 1 over 4 ohms times the same thing plus 0.5 dV by dt. So that's equal to this term here, which if I take to the other side becomes a positive 2. So I get a fourth of dV dt, a fourth of that, half of that, so I get dV by dt plus V over 2 is equal to 2. Now let's check that result. By letting t go to infinity, we don't have to assume that the input's constant because we know it is. It's just 2. So as t goes to infinity, V of t becomes constant. That goes away. So it's just V over 2 is equal to 2, or V of infinity is equal to 4 volts. We can check that against the circuit as t goes to infinity. And as t goes to infinity for a constant value, this becomes an open circuit. So that's V of infinity. This is now just a voltage divider, so that voltage is half of 8 volts, which is 4 volts, which agrees very nicely with our differential equation. Now we want to determine the initial and final values of V of t. For initial conditions, we have to take a look at the circuit before this switch moves. So circuit at t equals 0 minus, just before the switch opens, is this 8-volt source, 4 ohms, 4 ohms, 2 ohms with a short circuit up here, and the capacitor just before that switch opens, if we assume the switch has been closed for a long time, will look like an open circuit. So this is V at 0 minus. There's no current through here, so there's no current through either of those. So this is a voltage divider, and this becomes 8 volts times 4 ohms over 4 ohms plus 4 ohms, which is 4 volts. Capacitors can't change their voltage instantaneously, so the initial condition at t equals 0 plus is also going to be 4 volts, which is the same as V at t equals 0 minus. The final value we already found in the previous slide. Let's just go over it really quickly. So the circuit as t goes to infinity, we have an 8-volt source, 4 ohms, 4 ohms. This is an open circuit, and we have a 2 ohm resistor here. This is also an open circuit as t goes to infinity since the input's a constant. So V at infinity is a voltage divider. It's 4 volts. This doesn't really affect anything because there's no current through this guy here, just as there's no current through this guy here.